proof by contradiction. So proof by contradiction is a proof where you're trying to prove something is true. So what you do instead of trying to prove something is true, you say, well, it's false. And then, if it's false, then some things are going to already be, you can gather from something being false, other things follow. And from those logical things that follow, you try to show that the assumption of false leads to a contradiction. And if it leads to a contradiction, then assumption of something being false cannot happen. Which means that if the assumption of falsehood is false, then in fact we're just going to prove it's true. So we're going to look at an example. This is similar to one of the homework problems. We're going to prove that square root of 2 is not a rational number. But before we prove it, we should know what is a rational number. What is a rational number? Anybody?
B by 2.
So it's a ratio of two numbers, both of which are integers. Integers. So for example, is 1/3 a rational number?
Yeah.
Okay, even though it's 0.33333334, it's a rational number. Is 2,034 over 1,234,873, is that a rational number? Yes. How about negatives, integers? Sure, fine. Two negatives make a positive, one in a ratio make a negative, no problem at all. So yes, so those are all rational numbers. What is not a rational number?
Pi.
Pi is not a rational number, why not?
You can't represent it in the ratio.
What's the problem with pi? Why is it not a rational number? I mean, doesn't 0.333333 for 1/3 go to infinity? Doesn't pi also go to infinity with its number of decimal places? What's the difference?
Right as A by B, and A equals R.
Well, we cannot write it as the ratio of two integers, that's true. So, in fact, we don't know the precise value of pi. We can get pi to any number of decimal places of precision we want, but we cannot accurately say, this is pi, period. It never ends, it never terminates, it never repeats. So that's the problem. Give me another number that we think is going to be irrational. E, okay, you're getting all the famous ones, okay? How about the less famous ones? How about the plain old ordinary square root of 7? That's another one, right? Okay. So rational numbers, irrational numbers rather, cannot be expressed as a ratio of two integers. Cannot. Pi can't be, square root of 3 cannot be, square root of 5 cannot be, square root of 7 cannot be, square root of 11 cannot be. Those are all irrational numbers. So let's prove it. How do you prove it? Well, we want to prove that square root of 2 is not a rational number. So therefore, we want to prove that it is in fact irrational. Okay, so we're going to do by contradiction. We're going to say, well, let's assume that square root of 2 is rational. So if it's rational, we're contradicting or we're negating what we're trying to prove. We're doing the opposite. We want to show that it's irrational, we say, assume it's rational. Well, if it's a rational number, then it has to be expressible as a ratio of two integers. And those two integers we can choose are going to be A and B. So A over B would be radical 2, because if it's rational, it must be expressible by the definition of rational numbers, which is ratio of A over B, where A and B are elements of the integer set C. But furthermore, every rational number can be expressed as a ratio of A and B, so that A and B have no factors in common except for 1. So for example, is 4 over 8 a rational number? Yes, but it can be expressed as 1 over 2. Now, the common denominator of 1 over 2 is going to be just 1. Okay, same thing, 6 over 9. 6 over 9 is a rational number, but it can be divided by 3 on top, 3 on the bottom, and it's 2/3. No common factor except for 1. So every rational, now you may have some numbers like 3 over 17. 3 over 17, that's it. How come? No common factors other than 1, so we can't reduce further. So basically every number which is rational can be expressed as A over B in what we call simplest terms. We have no factor in common except for 1. So therefore, if radical 2 is rational, it can be expressed as A over B, where the common factor between A and B is only 1. Cannot be anything else. So we're going to say it's equal to A over B, where A and B have no common factors, again, except for 1. So, since from our assumption of rationality and our equivalence of radical 2 equals a over b, we have radical 2 is equal to a over b, and so now we can do things that are reasonable in terms of mathematics. So what we're going to do in this case, we're going to square both sides. Squaring radical 2 is 2. Squaring a over b gives me a squared over b squared. Okay, so I have 2 is equal to a squared over b squared. Now, multiplying, cross-multiplying, if you will, I get 2 times b squared is equal to a squared. Now, 2b squared is equal to e squared. That implies that a squared is even. Why? Because a squared is equal to 2 times b squared. Therefore, it's going to be even. So a squared is even. If a squared is even, that implies a is even. How come? A squared is even. If a squared is even, then a is even. But did we prove that before? Or are we supposed to just be geniuses and know that? Well, actually, we proved it. Didn't we? So, how do you prove that if a squared is even, then a is even? Well, we can prove it by inverse proof. Or indirect proof. What do I call it? Indirect? Indirect proof, not inverse. Indirect proof. Indirect proof. A squared is even implies a is even. So to prove that, you can say if a is not even, then a squared is not even. Well, if a is not even, a is, and if a squared is not even, a squared is also odd. And we proved directly that if a is odd, a squared is odd. Therefore, we proved, right, the indirect proof. So therefore, that means that if we prove that it's, right, so therefore we have a proof that if a squared is even, a is even. Does everybody follow what I just said? Does that make sense? Okay. So if we have this, so therefore, since we now know that a squared must be even because a squared is equal to 2 times b squared, and we know that a squared is even, we also know that a is even because we have already proved the fact that if a is not even, then a squared is not even from last class. So there we have a is even. So that's fine. That's an integer. It's even. Very, very nice. So now a, since it's even, we can write a as 2k, where k is any integer. Again, k is any value, any element of z. So a is even. A is equal to 2k. Therefore, 2b squared is equal to a squared. But a squared is 2k, so 2b squared is equal to 2k, just a substitution, squared, which is equal to 4k squared. So 2b squared is equal to 4k squared. And now we can divide by 2, and we get b squared is equal to 2k squared. Which means that b squared is even. Why? Because b squared is equal to 2 times an integer. And if b squared is even, that implies that b is even. By the same token as a squared is even implies a is even, b squared is even implies b is even. So the interesting thing is we're saying now that we have assumed that radical 2 is rational, and we said a over b is the lowest, the simplest way to do it without any common factor other than 1, our logic has just driven us to tell us that both a and b must be even. Which means that it's saying we're contradicting that we have this in lowest terms with a common denominator of 1. It says, no, you can't have that. You can't have that. But we know we can have that for any rational numbers. So therefore, we've contradicted that square root of 2 is rational because we saw that it cannot be expressed as a ratio of 2 integers with the greatest factor being 1. Why? Because a is even and b is even. So the factor now is 2. Well, this 2 is unacceptable because we said a and b, a over b does not have anything in common other than 1, factor of 1. So a and b have a common factor of 1. This is a contradiction that we can express it as any rational number in lowest terms. We cannot. So therefore, since we've contradicted our assumption of rationality, then we have proven that square root of 2 is not rational. And that makes it irrational. Okay, any questions on that? Okay, I have another proof by induction here. That's a good one. So here what we want to show is we want to show that n squared, or sorry, that n factorial that the function n factorial, and I'll write it here on the little sideboard here, as much as I can, we want to show that n factorial is less than n to the power of n whenever n is an element of what? Positive integers, z plus integers plus t positive. So for n element of z plus. So what's the first element of z plus? 1. What's the next? 2, etc., etc. Okay. So, so basically we're going to do this by induction. We're going to do this by induction. So the base case is, it says n greater than 1, n positive. So that means the smallest one can be what? 2. Because we say greater than 1, well, you can't have an integer greater than 1. That's 1, so 2 is the next one up, and it's positive, so 2. So the base case, all we have to do is plug in 2 for n everywhere we see it. So we get 2 factorial, which is 2 times 1, is going to be less than 2 to the 2 power. And that gives me 2 is less than 4. This is true. So we've directly proven the basis. This is what we do, we directly prove the basis. Okay. So now we go to the inductive hypothesis where we make the assumption. And in that case, all we do is take what we're going to prove and simply make a replacement for n with j and limit the value of j to be less than n, because n is purely general, and therefore we cannot just assume n. We have to say it's less than n, and then we have to prove it for n. So by assuming that j factorial is less than j to the j, for values of j less than n, and I said here greater than 1, but I really could say greater than what? 2, because 2 has been proven already, so we don't have to assume that. That's proven. But it's not wrong. It's not wrong. So, so now what we're going to do is, since we have that j to the j less than j factorial less than j to the j, what we're going to do is we're going to take that j to its maximum integer value. And since j has to be less than n at most, that means the biggest value less than n is n minus 1, and I'll use that value. So I'll replace j with its maximum limit value, which is n minus 1. And I'll get n minus 1 factorial is less than n minus 1 to the n minus 1. So this is our inductive hypothesis. So now what we're going to do is we can use the inductive hypothesis and rules of logic and mathematics to show that it holds true even when we increase it to n. So we take n minus 1 factorial less than n minus 1, and then what we're going to do is mathematically, now let's think about what we're doing here. What is the sign, S-I-G-N, what is the sign of n minus 1 factorial? Is it positive, negative, or 0? It's going to be positive because at the smallest value, again, I should probably put a 2 here, which means that j can be no less than 3, really. So 3 minus 1 is 2, 2 factorial is positive. And 3 minus 1 is 2 to the 2, that's positive. So I have positive less than positive. Now that's important because if I divide an inequality, by a negative number, or multiply by a negative number, the inequality switches. So we have to be sure that if we're going to be dividing and multiplying inequalities, we're always multiplying something that either doesn't switch its sign, or we switch the sign if it should be switched. But in this, so because what I'm going to do is I'm going to multiply this side and this side by n. So multiplying this side by n gives me n times n minus 1 factorial, and this side gives me n times, well, this, n minus 1 to the n minus 1. Now, of course, n times n minus 1 factorial becomes n factorial, which is very good because n factorial is exactly what we have on the left-hand side of our proof. However, the right side is not exactly what we have in our proof. The right side looks like n times n minus 1 to the n minus 1. So it's not exactly what we want, so we're not done with the proof, but we are closer to the proof. So now we have to think, which is always hard, what do we do next to complete the proof? How can we show that n factorial, which is less than this, is in fact less than that? And that's not too difficult, because what exactly is the right-hand side of the inequality? What exactly is the right-hand side here, which is n times n minus 1 to the n minus 1? That means it's going to be n multiplied by n minus 1 times n minus 1, n minus 1 times. And we know that these are all positive numbers. Again, it's important to keep in mind to make sure that we don't do anything that's going to flip signs on us, but it's not going to happen. And so what I'm going to show is, since we know that n factorial is less than this, and this is exactly this, now I can look back over here and say, well, n to the n power is actually going to be bigger than this, because it's what it is. It's going to be n minus 1 factors of n, which are 1 greater than here, and the same factor of n here. And since they're all positive, that means that this value will be even bigger than this value. So therefore, since n factorial is less than this, and this is this, which is less than exactly what we're trying to prove, then by transitivity, we have shown that n factorial is less than n to the n. And then this value is someplace in the middle. Does that make sense? So that wasn't like an easy one, because we had to do thinking, because multiplying simply by n did not work. Okay. And again, be careful if you have an inequality, if you're multiplying both sides of an inequality. If the number is not guaranteed to be positive, you could have a problem. So think about what number it has to be. And the reason I was sure it was going to be okay is because really I could have had a 2 here. J had to be at least greater than 2, which means the smallest value could have been is 3. If J could have been 0, then 0 minus 1, we would have some issues to worry about. But I'm not going to give you problems that are going to give you big issues. But just be careful that you're not doing anything that's improper in mathematics. Okay, any questions about that one? Let's do something that's a little bit computer science oriented. We are all familiar with something known as a binary tree. So a binary tree is a tree, or it's a set of nodes where nodes can have children, and children have a parent. So you can see over here, we have, what do we call this on top of the tree? That's usually referred to as the root, and then we have the left child, and the right child, and this child, and its own child, and another child, and this child, and its own child, and another child. So this is a binary tree. Binary means that each node can have at most 2 children. Okay, so the height of this tree, we're going to say is 4, and the height of the tree will be, you can typically count it, we'll call all the nodes here that we see here, we'll call those internal nodes. Internal to what? Internal to the tree. So what are external nodes? External nodes are the little null pointers at the end, which sort of add something but don't really add any real nodes. So you can think of it as the height of a tree is the number of steps to the furthermost external node. So if you go here, I make 1 step to the internal node, 2 steps to internal, 3 steps to internal, and then 4 steps to the external node. So you can think of it, that could be defined as the height of a binary tree. Okay, so the height is equal to 4, and what we want to prove that the tree with a height of n, in this case n is 4, the height of n has less than or equal to 2 to the n minus 1 leaves. What are leaves? Those are the nodes in a tree that have 0 children. They don't have children. So that's what leaves are. So we want to show that if a tree is binary and has a height of n, it has less than or equal to 2 to the n minus 1 leaves, or we can say that it has at most 2 to the n minus 1 leaves. So we're going to try to solve this. We're going to do this by induction, again. So we will let the maximum number of leaves on a binary tree of height n be Ln. So I'll define a function Ln. L for leaves. Ln will be the maximum number of leaves in a tree of height n, Ln. And so what we want to do, in a sense, is to show that Ln is less than 2 to the n minus 1 power. So the base case occurs when the tree is, for example, L of 1. So that means the height here is what?
1.
Height here is 1. Now you can say, well, wait a second. Is that really the base case? We could have a tree that what? That has 0. So if I start with 1, that means I am not covering 0. So maybe I should cover 0. But I'm just telling you, my proof will not include 0. But 0 can be proved directly if you want to. So we can start with, so So L1 is less than or equal to 2 to the 1 minus 1, which is 2 to the 0. Well, 2 to the 0 is 1, so L1 is equal to 1. Now this is true because a tree of height 1 has at most one leaf. Well, in this case it also has at least one leaf. So a height of 1, because it means it only has a root. So the root is also a leaf, has no children. Now notice that I have more shaded in here, and I can try to show L2 is true. But I put it in gray, and the reason I put it in gray is because it's not necessary for me to do it. Because to do a proof by induction, I do not actually have to show L1, L2, L3. I can just show basis, assumption, and then go to the proof step. But sometimes we feel better about ourselves if we show the next step because it makes us feel, oh, it's true for 1, it's true for 2, so it's probably going to be true. Especially if I give you a question on homework or on a test in which I say, prove or disprove this statement. So if, for example, L1 was true but L2 is false, you can say, it's false. I can't prove this. This is a false statement. It is not true. So if you're going to disprove something, you might want to try that. But for the proof, it's really not necessary. So I'm going to skip it, but you can certainly see what I'm showing you here. So this is a tree of height 2, and you can see that a tree of height 2 has how many leaves here? 2, but I could cut one of them off. It would still be a tree of height 2, and it would have 1 leaf, which is certainly less than or equal to 2. So it's correct. So we can see that this is still correct, so it's worthwhile pursuing further. So our inductive hypothesis will be to assume that the number of leaves in a tree of height k, just substituting k for n, is less than or equal to 2 to the k minus 1, where I'm going to let k vary from 1 less than n. And of course, I don't really have to have 1. I could just say greater than 1. Or if I include this, I can say greater than 2. You understand, right? Okay, so now so that's our inductive hypothesis. So now for the proof step, suppose we have a tree of height n minus 1. If we have a tree of height n minus 1, that means k is equal to n minus 1. N minus 1. So therefore, L of n minus 1 is going to be less than or equal to 2 to the n minus 1 minus 1, which is 2 to the n minus 2. So that's, we maximized our assumption. But the tree, the height of this tree is only n minus 1. So the number of leaves is less than or equal to 2 to the n minus 2, which tells us that the maximum number is 2 to the n minus 2. So that's how many leaves we have. So now, how do we transform this tree of height n minus 1 to a tree of height n? Well, we need to add a level. And we can add a level to every single leaf node. So therefore, we're going to grow the tree by 1 level, and each existing leaf can produce 2 new leaves. So from 1 leaf on the bottom, like over here, look at this leaf, I'll produce a leaf and another leaf. So essentially what happens is each leaf doubles the number of leaves. Because they have no children, I'm going to give them 2 children. If we grow the tree by 1 level, each leaf can produce 2 new leaves. Therefore, Ln is less than or equal to 2 times Ln minus 1. But Ln minus 1 is 2 to the n minus 2. So 2 times that is 2 times 2 to the n minus 2, which is 2 to the n minus 1, which is what we're trying to show. So as we grow the tree, we produce this. Okay, I'm going to skip this one. This is in the notes, but I'm going to skip this example. Again, you can take a look at it yourself. I'm going to skip this one. It's also a good one. This is a strange one because it's very, very interesting. You need a few base cases here. You can see the basis. We need like 4 basis cases in order to establish the proof. So that's kind of an odd one. So now what I want to do is I want to argue a little bit about why induction is a valid proving technique. Because we've been doing it, but it's kind of strange because what we're doing really is we're saying, okay, let's prove the very first type, first value. Let's assume for all values bigger than that, less than n, and then we'll just show that it's also for n. We'll say proof, that's it, we're happy about it. But why is that valid? So for that, we're going to prove induction. We're going to prove that induction is correct, proving technique. We can't prove it by induction, we can't prove it directly, but we will prove it using contradiction. So we're going to say, we're going to try to prove induction works by trying to argue that induction doesn't work and showing that that assumption leads to a contradiction, which means that induction in fact works. So, the theorems that we're proving with induction oftentimes want to show that P, some statement, is true for all values n, and typically n is like some starting integer and grows indefinitely towards infinity. So many theorems say that P of n is true for all, for example, positive integers, or 0 and the positive integers, or from 3 to infinity of integers, etc. So theorems are trying to prove this, typically by induction. And you've seen it before. Here we try to show that we are looking at the height increasing from 1 to infinity, and we proved it, right? Here we're trying to show that n factorial is less than n to the n for integers greater than 1, 2, 3, 4, 5, 6, up to infinity. Okay? We also showed that the summation of, as I goes from, let's say, 1 to n, of 2 to the I is equal to 2 to the n minus 1. So we've done that. So again, everything, so we're moving our values of n from some starting point, the basis, up through, up towards infinity. And we use induction to prove it. So how is this induction in fact correct? Well, induction states that if we know P1 is true, what does that mean? If we know P1 is true, what step is that? That's the basis step. And we prove that directly. We just plug stuff in, see if it's true. So therefore, the first step is that P1, and again, I'm using P1, if we're going to use positive integers, I'm going to use P1. Of course, we could use P0 if we want 0 and include the positive integers. But the induction basically states that the basis, P1, is true. And then we have a implication which says Pn implies P of n plus 1. That's really what we have. Because when we say that for j greater than some basis less than n, what we're saying is that P of n implies P of n plus 1. It's true. So this is our assumption. And we're saying that if this is true for all positive integers, that implies P of n is true, and this means for all n values in the positive integers. So again, we're trying to show that P of 1 is true, basis, and P of n implies P of n plus 1. Where P of n is our assumption, and P of n plus 1 is our proof step. In fact, you can think of it as, you can read this as, if P of n is true, then P of n plus 1 is true. That's really what we're doing when we move from the assumption to the proof. We take that maximum step at n minus 1 and we go to n. Likewise, you can go from n to n plus 1. It's the same idea. Makes no difference. You just need to go from some limit to just one more. And if you can show that, then we're saying it's true. So let's write this a little more technically using some logic notation. It's very simple, but it looks very strange, so I'll make it very clear. So what we have here is, so first of all, let me make sure you understand this. So the A upside down is not a typo, it just means for all n, for all positive integers n. So that's for all n. So we can read the part in the brackets from here to here that if P of 1 is true, or P of 1 being true, and for all n, P of n being true implies P of n plus 1 is true. If those two things are true, that implies that P of n is true for all n. Now I'll do this a couple more times until I can hit the right English wording that makes you happy. So we're saying that P of 1 being true, which is the basis, and for all n values, which means for all j values less than n, for all n values, if this is true, then this is true. So for all n values, P of n implies P of n plus 1. And again, this implication is what we're doing from the assumption to the proof. So if we're saying if this is true, and if our assumption implies P of n plus 1 is true, then that's sufficient to prove that P of n is true for all n. That's what a proof by induction breaks down to. So we're going to try to do a proof of this statement. Because if we can prove the statement is true, then we know we can show the basis. We can take an assumption and show that assumption can be extended to one more. And then if we can do that, then we've proven it and it's valid. And we're happy and we're graduate students and we're saying we get it. We'll explain it to you. All right, so we're going to prove this statement is absolutely true. And if we can prove that this statement is absolutely true, then induction is absolutely a valid process. And we're going to use contradiction, because obviously we can't use induction to prove induction. That would be wrong. Okay. That would be something we call begging the question. Please believe us. You have to believe us. It's true, it's true, it's true. Well, it's not true until it's proven, and you can't prove something by using the argument itself. Okay, so we are going to use something called the well-ordering property as an example. So the well-ordering property is very simple. The well-ordering property basically is talking about a set of non-negative integers. Non-negative integers include 0, 1, 2, 3, any combination of any number 0 or higher as integers. If the set is of non-negative integers and it is non-empty, then by definition it has what we call a least element, the smallest element. If I have a set of integers which are 0 and higher, any one of them you want, I know that I have a smallest element. Would you agree with that? Okay. I think that's a very clear, simple idea. The set is not empty, and the smallest integer can have 0. Well, then 0 is the smallest. But if it doesn't have 0 and has 1, well, 1 is the smallest. Well, if it doesn't have 0 and 1, and you have 2, then 2 is the smallest. Well, if you don't have 0, 1, or 2, well, then it's not empty, so you got something. If you got only one thing, well, that's the smallest. If you got 25 things, sort them. The smallest is the smallest. It's a set. They have to be unique. So we have what we call a least element, a smallest element. Okay, so this is what we call the existential qualifier. Exists. The upside down A is the universal qualifier for all. There exists one. So we are going to assume there exists a positive integer where P of n is false. So we're going to contradict this. Because basically we know that this alone, this is induction. And we're saying if we do the induction, if the induction shows true, that implies that it's true for all cases. We're going to say,